Welcome back to the deep dive. Today, we are attempting to map the inner universe.
Which is no small task.
No, not at all. We are tackling consciousness, but not through philosophy or, spirituality. We're looking at it through the really rigorous lens of geometry and information theory.
Mm-hmm.
Because for decades, researchers have given us these theories about what the brain does. It computes, it predicts, it processes information.
Right, all these functional descriptions.
Exactly. But those theories, they really struggle to capture the actual structure, the fundamental shape of subjective experience itself.
And that gap, that's often called the explanatory gap, right? The gap between the physical brain and the felt experience.
I think that's the perfect way to put it.
The core issue is that we have what are called neural correlates. So we know which parts of the brain light up when you see the color red, for example.
We can see it on an fMRI.
We can see it.
Yeah.
But what we lack is a formal, testable mathematical structure for the feeling of being conscious, for the redness of red.
And if you think about it this way, the feeling of the color green is distinct from the feeling of, say, nostalgia.
Completely different worlds.
Right. And, intuitively how similar or dissimilar those experiences are. But how do we encode that similarity mathematically?
Are those 2 points close together in your internal space? Or are they miles apart? That's the question.
And that's where this new framework comes in.
The phenomenal manifold hypothesis, or PMH. It's a structural framework that's designed to answer precisely that.
So this is a deep dive into computational neuroscience.
It is. And it says, you know what, let's set aside the philosophical hard problem of why experience exists at all. Let's forget that for a moment.
Okay.
Let's focus instead on modeling conscious experience as a quantifiable geometric object, a smooth structure called the phenomenal manifold, which is symbolized as psi.
So our mission today is, well, it's ambitious, but it's clear. We need to understand the fundamental geometry of consciousness. We're going to explore how 3 distinct, measurable properties of your brain activity combine geometrically to sculpt this phenomenal landscape.
And crucially, how this idea stands in direct opposition to some of the established giants in the field.
Like integrated information theory or IIT.
And global neuronal workspace theory, GNWT. This isn't just a new idea, it's a direct challenge.
So to get us started, let's land on that core analogy. Imagine every distinct sensation, thought, or emotion you have ever felt.
Every single one.
As a single dot in a vast, multidimensional space.
Okay, I'm with you.
The manifold, psi, is the total space that all those dots inhabit.
And the geometry of that space means something.
Exactly. So if the distance between the dot for tasting salt and the dot for tasting sugar is very, very small, that short distance reflects their phenomenal similarity.
They're close in experience, so they're close in the space.
But if the dot for tasting salt is really far away from the dot for hearing a trumpet,
Which it should be.
that distance encodes their dissimilarity. This is sort of a shortcut to being well-informed about the literal structure of your own subjective reality.
It's mapping the mind. Literally.
Okay, so let's unpack this geometric structure. The source material defines the phenomenal manifold, psi, as a smooth geometric structure. Why does that word smooth carry so much weight here?
Well, when mathematicians use the term smooth or differentiable manifold, they're implying a tremendous amount of mathematical structure. It's not a casual term.
It's very specific.
Very. It means that if you zoom in really, really closely to any single point in this space, let's say the experience of a specific shade of blue, that local region looks and behaves like normal Euclidean space.
Ah, okay. It's like looking at a small patch of the Earth's surface. The Earth is curved, but a tiny patch of it looks flat to us.
That's the perfect analogy. And this local flatness is what allows us to apply calculus. It lets us define things like continuous change or velocity, what they call phenomenal flow.
And most critically, a metric, a way to measure distance.
Precisely. If experience were jagged or non-continuous, meaning small neural changes cause these massive, unpredictable, phenomenal shifts, we couldn't use any of these mathematical tools.
The whole system would be chaotic.
Right. Smoothness guarantees that small changes in the brain's physical substrate, which they call M4, result in small, predictable changes in the experience, psi.
And speaking of M4, the physical substrate, the geometric shape of psi, its hills, its valleys, all the twists and turns, is determined entirely by the neural information dynamics happening there. When the theory talks about M4, What are we actually talking about? Is it just neurons?
It's defined pretty broadly as the physical system capable of supporting consciousness. So that usually means the thalamocortical system,
Yeah.
the cortex and the thalamus working together.
Okay.
But, and this is a crucial point, the PMH isn't just looking at the neurons themselves firing, it's looking at the information dynamics.
What does that mean, dynamics?
It means the flows of information, the causal relationships, the complexity, the patterns within that neural network. It's a higher level of abstraction.
Got it. And the mathematical core of this whole thing is something called the Riemannian metric, GPTSI. This is more than just a ruler, right?
Oh, much, much more. A Riemannian metric is the mathematical rulebook for distance in a curved space.
Okay.
It's not a simple straight line.
Okay.
It tells you point by point how to calculate the shortest path, the geodesic between any two experiences. So you want to know how similar anxiety is to boredom in a way that respects the curvature of your emotional landscape.
The specific twists of your personal mind space.
Yes, the metric GPSI is what you use. Without it, psi is just a scatter plot of points. With it, it's a measurable, rigid space.
Now, a complex space like this, theoretically, it could have an infinite number of dimensions. But the PMH insists on something called an intrinsic dimension, labeled N.
It does, and this is really important.
Why is determining this dimension so critical, and how do they avoid just, guessing a number?
The intrinsic dimension, N, is the minimum number of independent parameters you need to capture the essence of the experience space.
So the fundamental degrees of freedom.
Exactly. If we find that N equals 10, it means we need 10 coordinates, 10 unique axes of variation to accurately describe every possible conscious moment. It's an empirical number, not a guess, and finding it is a huge challenge.
So how do they ensure rigor here? How do you actually find them?
They demand what they call a consensus criterion. They don't just rely on one algorithm, which would be risky. They combine multiple mathematical estimators.
Such as?
Things like the correlation dimension, which looks at how the number of nearby points scales with distance. They use PCA, principal component analysis, which finds the main axis of variance. And they use something called isomap residual variance.
And they're looking for where all these different methods agree.
Yes, they're looking for where the curve elbows out. They're essentially trying to find the sweet spot.
The lowest possible dimension that still lets them reconstruct the full set of subjective relationships, but without introducing a massive amount of error.
You've got it. They have a strict rule.
Yeah.
N is found by minimizing the reconstruction error, but it's penalized by the dimension size.
So you don't want to just keep adding dimensions for tiny gains.
No. If adding an 11th dimension only reduces the error by a tiny fraction of a percent, but it makes the model way more complex, they stick with 10. And they require that all those different estimators agree within a very narrow tolerance, say plus or minus 2 dimensions, before they'll accept the finding.
That's methodological self-accountability built right into the framework.
It has to be.
That makes the geometry feel much more grounded. But for this whole structure, for psi to even exist as a stable, smooth, geometric space, it has to obey some fundamental rules. They call them the psychophysical axioms.
Yes, this is the bedrock.
Let's start with the first one, local discriminability.
Okay, this is a mathematical necessity for separation. It sounds complicated, but the idea is simple. If you have two experiences, A and B, that are infinitesimally close in the manifold.
Like two almost identical shades of gray.
Perfect example. You must still be able to discriminate between them, to tell them apart, above a certain probability threshold. They call it theta, and it's usually set somewhere between 50% and 100%.
And if you couldn't tell them apart?
Then they would have to be the exact same point. The structure would collapse because you couldn't define distinct little neighborhoods around each experience. It prevents all the points from becoming, well, smeared together.
Okay, that makes sense. The second axiom is psychophysical continuity.
This one ensures the map between the physical brain and the experience is stable and well-behaved. It requires that small, continuous changes in the neural information structure must map onto small, continuous changes in the phenomenal configuration.
No sudden, giant leaps in experience from a tiny neural tweak.
Exactly. And this is crucial because it ensures the manifold is smooth, which we talked about. Furthermore, the relationship has to adhere to established laws, like Stevens's power law or the Weber-Fechner law.
So it connects back to existing science.
It links the geometry directly back to literally centuries of psychophysical experimentation. It's not operating in a vacuum.
And the third, which sounds like it's there to keep the geometry from becoming illogical, is approximate transitivity.
This is vital for any valid metric space. Transitivity just means that distances have to be sensible.
Okay, an example.
If experience A, let's say seeing red, is very similar to B seeing orange, and B is very similar to C seeing yellow, then A cannot be wildly dissimilar to C. The distance between red and yellow has to remain constrained.
So it prevents nonsensical outcomes, like finding that the experience of seeing red is somehow geometrically closer to the experience of feeling a headache than it is to seeing orange.
Precisely. Without that constraint, the metric GPC psi would give you distances that violate basic psychological intuition. It would be useless for modeling reality.
So these three axioms, discriminability, continuity, and transitivity, are the mathematical constraints that really lift the phenomenal manifold from just being a metaphor
Into a scientifically viable, testable object. That's the goal.
Okay, we've established the target, this geometric object, the phenomenal manifold psi. Now we need to look at the ingredients the brain is using to cook up this geometry.
Right. What are the building blocks?
The PMH proposes that the geometry of consciousness isn't defined by just one thing. It's a unique combination of three key informational invariants, all derived from neural activity.
This is a major departure from other theories.
Let's start with the first one, the one that's probably most famous in this field, information integration, or I.
I measures the irreducibility of the system. That's a bit of a mouthful, but it quantifies how much information the entire system generates that cannot be accounted for by just summing up its individual parts.
So it's the wholeness factor.
It is. The classic thought experiment is, if you cut the system into two parts, how much information is lost in that cut? High I means the system functions synergetically as a truly unified whole.
Now, we know this concept is central to integrated information theory, where it's quantified as phi.
It's the heart of IIT.
But the PMH immediately pivots to address what's really a core computational crisis in the field.
Yes, and this is where PMH distinguishes itself by being incredibly pragmatic. In theory, I is integrated information, phi. The definition is the same.
In practice.
In practice, calculating the exact phi for a real-world system, like the human brain with its billions of neurons and trillions of connections, it's computationally intractable. It scales exponentially.
It's a computational nightmare. You just can't do it.
You can't. So, to make the PMH testable today, with real EEG or fMRI data that we can actually collect, they rely on readily computable proxies for tractability.
So they're approximations.
They are. Instead of exact phi, they use measures that capture the essence of integration, but are far, far easier to compute.
Can you give us some examples of these proxies?
Sure. The PMH uses things like the average mutual information across bipartitions. That just measures the average statistical dependence between different halves of the brain.
Okay.
They also rely on something called neural complexity, or NC, which essentially measures the trade-off between how differentiated and how integrated the system is.
A balance between the two.
Right. And also causal density, or total Granger causality, which quantify the density and flow of cause and effect relationships within the network. These proxies allow the theory to be falsifiable right now.
Even if they introduce some systematic error compared to the theoretical ideal of phi.
Exactly. It's a practical trade-off.
So IA is about unity and synergy. Let's move to invariant 2, global coherence, or gamma. Why do we need coherence if we already have integration? Don't they sound similar?
They sound similar, but they capture very different properties. Integration is about the content and the statistical dependence of the information flow.
Okay.
Coherence, gamma, is strictly about the timing and the rhythm. It measures large-scale phase synchronization across distributed neural populations.
So how tightly locked the brain's electrical oscillations are with each other?
That's it. This suggests that a brain could have very high content integration, but if the timing is chaotic, the experience might still be fragmented or disorganized.
I see. So gamma is the glue for temporal organization. It keeps everything in sync.
Precisely. Mathematically, it's defined using something called the Kuramoto order parameter, which looks at the instantaneous phases of neural oscillations, usually in specific frequency bands like alpha or gamma.
And it's a simple scale.
It is. Gamma ranges from 0, which is random chaotic timing, to 1, which is perfect, locked synchronization. The PMH posits that high gamma is crucial for a unified, smooth, phenomenal geometry, ensuring temporal stability.
That brings us to the third leg of the stool, invariant 3, informational differentiation, or delta. We have unity from I, we have synchrony from gamma, and now we need diversity from delta.
And you need all three. Delta is the repertoire size. It quantifies the sheer diversity and complexity of accessible informational states the system can actually achieve.
So it's like the depth and breadth of the system's dictionary.
That's a great way to put it. If your brain can only cycle between, two or three basic states, sleep, wake, slightly sleepy, your delta is very low.
But if it can access millions of unique, complex, never-before-seen configurations.
Then your delta is high. It reflects the richness of conscious content. If you are experiencing high complexity, a symphony of color, sound, and emotion, your differentiation should be high.
And how do they measure that?
They use established tools like Shannon entropy, which measures predictive uncertainty, or something called Lempel-Ziv complexity, which measures the computational complexity of binary sequences derived from the neural activity.
So the critical insight here, which really challenges some of the simpler single-factor theories, is that a truly rich conscious state requires a dynamic equilibrium.
Yes.
You need high I for the unity of self, but you must also have high delta for the richness of the experience.
Absolutely. A system with high integration but low differentiation. It's like a computer that's perfectly connected, but it only runs a single program.
It's unified, but the experience is simple and impoverished.
And a system with high differentiation but low integration is like 1,000 unconnected computers. Vast potential, but no unified single experience. The phenomenal manifold psi gets its complexity and its volume from the co-occurrence of all three of these factors.
So we know the ingredients now, I, gamma, and delta. And we know the target shape we're trying to create, psi. The next challenge is the recipe.
The how.
Exactly. How does the brain mathematically cook those ingredients into that specific geometric shape? This is where the smooth projection map pi comes in.
The map pi is the necessary bridge. It's a mathematical function that takes a specific neural informational state, let's call it S, which is a point in the very, very high dimensional neural space.
P of M4.
Right. And it projects it smoothly down into a specific conscious experience, CI psi, which is a point in the much lower dimensional phenomenal manifold.
And the source material provides some really compelling justifications for why this map pi has to work. Let's start with the most fundamental one, the information theoretic constraint.
This is dictated by something called the data processing inequality. It's a law of information theory. It's non-negotiable.
Okay.
It states that you cannot possibly gain information by simply processing existing information. And when you apply that to consciousness, it means phenomenal distinguishability cannot exceed neural informational distinguishability.
In simple terms.
If your brain can't distinguish between two neural states, you certainly can't tell the two resulting experiences apart. Your experience can't be more detailed than the information that creates it.
And what does that mean for the map pi itself?
It forces pi to be what's called Lipschitz continuous. This is the mathematical term for smooth or bounded. It means the map can't suddenly generate massive phenomenal distances from tiny, almost indistinguishable changes in the neural input.
The map has to be stable.
Yes. The phenomenal structure is fundamentally constrained by the information content of the physical substrate.
The second justification gets at the inherent redundancy in the neural system. It's called invariants under phenomenal equivalence, or the quotient structure.
This is a really powerful realization about how the brain manages complexity. Just think about how many slightly different ways your visual cortex can fire, and yet you still perceive the exact same shade of pure green.
Right. There must be countless neural patterns that all result in the same experience for me.
Exactly. Those slightly different neural states, S1, S2, S3, are all phenomenally equivalent. They feel the same.
So the map needs a way to collapse all those redundant neural states down into a single phenomenal point.
That's what a canonical quotient map does. The projection pi is a quotient map. All those phenomenally indistinguishable neural states are bundled together into what the PMH calls a fiber structure in the neural space, and these entire bundles map to a single point in psi.
So the structure of these converging fibers mathematically encodes phenomenal indistinguishability.
It does. It's the mechanism by which the immense complexity of the brain is reduced to the minimal, essential complexity of the experience itself.
And finally, there's the variational characterization. This is the mechanism by which we can actually find this optimal map in the real world.
Right. This just states that pi is the optimal solution in an optimization problem. It's the map that minimizes the error between the predicted phenomenal configuration based on the neural data and the reported phenomenal configuration from the subject.
All while obeying the constraints of smoothness and dimensional reduction we just talked about.
Exactly. In practice, researchers use machine learning to find the best fit pi.
All of this scaffolding leads us to the core mathematical statement of the theory, the central equation for constructing the hybrid metric. This is the moment where the local and the global factors collide.
This is the equation that defines distance in our manifold. It's GPSI equals pi star G info plus H of I, gamma, and delta. It says the phenomenal metric is composed of two primary factors.
Okay, let's break that down. The first factor is the local constraint, pi star G info.
Right, that's the pullback, the Fisher information metric from the neural space.
The Fisher what?
The Fisher information metric. It's a tool from statistics that's fantastic at measuring local distinguishability in the brain, how easy it is for the neural system to tell apart two nearby inputs.
Okay.
The pullback simply means we are projecting that local distinguishability measurement onto the phenomenal space. This ensures that the distance between red and orange is locally consistent with how easy it is for your visual cortex to tell them apart.
But local distances aren't enough to define the whole of consciousness. That's why the PMH introduces the second component, this crucial perturbative correction term, H of I, gamma, delta.
H is the global factor. It's a mechanism that allows the large-scale state of the brain, its integration, its coherence, its differentiation, to globally shape the entire geometry.
So it adjusts the whole map based on your overall state.
Precisely. For instance, if you increase your differentiation, delta, meaning your state repertoire, gets vastly richer, as it might under psychedelics. The metric GPSI must expand globally. This results in a larger volume of possible experience, regardless of what the local discriminability is doing.
And the constraints on the coefficients alpha, beta, gamma that weight the invariants I, gamma, and delta, they aren't just for mathematical elegance, are they? They have profound phenomenological meaning.
They absolutely do. They ensure the math aligns with our intuition. The first constraint is normalization. If I, gamma, or delta drop to zero, like in deep sleep, then their associated contribution to the metric has to vanish.
Makes sense. If there's no diversity, the diversity term can't expand the manifold.
Exactly. The second, and maybe the most meaningful, is monotonicity.
What's that?
It means that the coefficient functions have to be monotonically increasing. Increasing any of the three invariants, integration, coherence, or differentiation, must expand the phenomenal space.
That confirms the intuitive link. More unity, more synchrony, or more diversity results in a richer, larger, more complex, subjective world.
And this constraint is critical for clinical applications. It guarantees that as a patient emerges from a coma, for example, and their I and delta increase, the measured volume of their phenomenal space must grow. It provides a clear directional marker for recovery.
And finally, boundedness, which prevents the metric from becoming physically nonsensical.
Right. They have to be bounded within physiological limits to prevent the metric from exploding to infinity. The plausible functional forms they suggest in the paper inherently respect this. By requiring the local Fisher metric to be positive semi-definite and the correction term H to be positive definite, the resulting GPC psi is mathematically guaranteed to be a valid Riemannian metric.
So the geometry of your experience is the sum of constrained local precision and globally modulated complexity.
That's a perfect summary.
We've laid out the theoretical framework, it's elegant, but now we have to confront the actual scientific engineering.
Messy part.
The messy part. How do we build this map, pi, and the manifold psi from real people and real brain data? This is where methodological rigor truly matters.
Indeed, the PMH is useless if we can't operationalize the mapping. The procedure involves three critical empirical steps that have to be carried out in parallel.
Okay, step one, neural state space reconstruction, or NEMP. How do we turn a flood of raw brain data into a manageable, measurable state space?
We start with high-density neuroimaging, fMRI, EEG, to capture activity patterns under various conditions, viewing different stimuli, performing different tasks.
And this raw data is huge, thousands of variables.
Way too complex to analyze directly. So we apply sophisticated nonlinear dimensionality reduction techniques, things like isomap, UME, or diffusion maps.
And these tools embed the high-dimensional neural activity into a lower-dimensional empirical neural space, NM.
Exactly. This NM is the measurable representation of the brain's informational capacity that we can actually work with.
Okay, so that's the brain side. Step two is the most challenging because it requires us to quantify something that is fundamentally subjective, phenomenal space reconstruction, or PSYEMP.
This is the subjective anchor of the entire framework. It's where the rubber meets the road. Researchers have to collect systematic, quantitative phenomenological reports.
How do they do that?
The preferred method is generating a pairwise dissimilarity matrix. So, for instance, subjects might be asked to rate the dissimilarity between 50 different color patches, or 50 different emotional states, or 50 musical tones. How different is this from this on a scale of 1 to 10?
And this is where I have to press you. If consciousness is supposed to have this universal geometry, how can we trust these reports? I mean, people use wildly different words and internal scales for experiences like sadness or nostalgia or even color.
Hmm.
Doesn't the reliance on subjective reporting threaten the supposed objectivity of the manifold?
That is the single greatest empirical challenge, and the PMH addresses it head-on through validation and consensus. First, they use statistical methods, primarily multidimensional scaling, or MDS, on that dissimilarity matrix.
What does MDS do?
It takes all those reported subjective distances and tries to arrange the experiences in a low-dimensional space, Psi-Emp, that best preserves those distances. It finds the best fit map.
But what ensures these MDS maps are actually valid and comparable across different people?
This is where the validation becomes multi-layered. First, they demand the reconstruction be highly predictive of held-out data. The out-of-sample prediction correlation has to be above 0.7, which is a high bar.
Okay.
And critically, they mandate cross-subject consistency. If you have 10 subjects map the same set of 50 colors, those 10 individual maps have to be geometrically aligned through a procedure called Procrustes transformation.
And the distance between them has to be minimal.
Very minimal. They set a threshold, for example, a Procrustes distance of less than 0.3. This statistical consensus criterion ensures that the geometry that they capture is robust and not just an artifact of one person's reporting style.
And if the maps failed to align across subjects?
The entire premise of a universal structure would collapse. The theory would be falsified right there.
That statistical check really helps stabilize the subjective input. So once we have the neural map, NEMP, and the phenomenal map, Psi-Emp, we move to step 3, learning the mapping, pi.
This is the machine learning step. We train an algorithm to find the specific function, which we call pi hat, that translates NEMP to Psi-Emp. And they suggest using advanced techniques that are sensitive to complex, nonlinear relationships.
Like Gaussian process regression.
Exactly. Gaussian process regression is excellent for this because it provides not just a single map, but a probabilistic distribution of possible maps. It allows for uncertainty quantification.
And you can control for smoothness.
You can. It allows for geometric regularization, meaning we can mathematically penalize maps that are too jagged or complex, which enforces the necessary smoothness of pi.
And the alternative they suggest is optimal transport.
Optimal transport is a powerful geometric tool. It minimizes the cost of moving the entire probability cloud of the neural data onto the probability cloud of the phenomenal data. It finds the most efficient, smooth transformation that preserves the overall structure. It's very principled.
Now, given all these choices, different proxies for I, different estimators for N, various fitting algorithms, the theory seems vulnerable to the risk of overfitting,
A huge risk.
where the model only describes the specific data set it was trained on. How does the oversitting prevention protocol maintain scientific accountability?
This protocol is really a hallmark of rigor in the PMH framework. It starts even before they collect any data, with the pre-registration of all hypotheses, all analysis pipelines, and all parameters.
So you can't change the rules mid-game.
No moving the goalpost.
Yeah.
Then, the data has to be split rigorously. Strict data splitting. 50% for training the map pi, 25% for validation and tuning the hyperparameters, and 25% held in reserve for the final, completely untouched testing phase.
And any model that performs poorly on that test set is rejected.
Immediately, regardless of how well it performed in training.
But the truly specific part of this protocol is the complexity penalization using the Bayesian information criterion, or BIC.
This is essential for ensuring mathematical simplicity, for finding the most elegant solution. The BIC penalizes models that have more free parameters.
And they have a strict rule for it.
A very strict criterion. They only accept a more complex model, say one adding a nonlinear coupling term between I and delta in that H metric, if the evidence is overwhelmingly strong. Specifically, a change in BIC greater than 10.
What does that mean, a change of 10?
A difference of 10 points means the complex model is vastly more probable than the simpler one. It provides robust evidence that the added complexity isn't just a statistical quirk.
And finally, the requirement for independent replication.
A finding is only accepted as robust if it can be independently replicated in a second dataset. And ideally, that dataset is collected in a different lab using a slightly different population or even a different imaging modality. This whole protocol forces the PMH to build structures that are truly universal, not just descriptive fits of local data.
Now that we know how to measure the geometry, let's explore what the shape actually means. How do different states of consciousness map onto this manifold psi?
Right. How do the three geometric levers, I, gamma, and delta, sculpt the experience?
The shape is defined by its intrinsic dimension n, its curvature, and its volume v.
Exactly. Volume is the total capacity of possible experiences. And different combinations of the three invariants define distinct, measurable regions in psi.
So let's start with our default state, ordinary wakefulness.
Wakefulness is the complex baseline. In this state, we have high, we feel unified as a self. We have moderate gamma enough coherence for organized thought, and moderate delta, a diverse but still constrained repertoire of thoughts and feelings.
And what does that look like geometrically?
Geometrically, this translates to a high-dimensional region they typically estimate to be in the range of 8 to 15 dimensions.
So a lot of degrees of freedom.
A lot. It has moderate dynamic curvature, which reflects the constant flux and change in complexity of our everyday thought processes and incoming sensory data. This is the largest integrated and coherent space we generally inhabit.
What happens when we lose consciousness, like in deep sleep or anesthesia?
So in that case, all three invariants just plummet. Low I, low gamma, low delta. And when this happens, the geometry itself collapses.
The space shrinks.
It shrinks toward what are called degenerate submanifolds. We see a near-vanishing metric structure, which means the phenomenal distances are tiny, reflecting almost no experiential difference between one moment and the next.
Yeah, and the dimension.
The dimension plummets dramatically. It typically falls somewhere between 1 and 3. The conscious space effectively collapses to a minimal point or a line.
Okay, now let's jump to the extreme opposite end of the spectrum, psychedelic states. The subjective reports often involve a massive expansion of the perceptual field, profound complexity, things people can't even describe.
And this maps perfectly onto the PMH geometry. Psychedelic states are characterized by very high delta, a massive increase in entropy and the number of accessible states.
Right.
Integration is variable. It can feel unified or sometimes fragmented. And often, global coherence, gamma, is actually reduced compared to baseline.
And this combination results in a geometric expansion.
It's like you're opening up a previously locked wing of the manifold.
A whole new area of the map becomes accessible.
Exactly. The manifold expands into regions of high curvature and very high volume, which reflect that subjective novelty and complexity. The dimension skyrockets, potentially reaching an end between 15 and 30.
Wow.
Imagine moving from a small local library to an infinite Borges library. That expansion in scope and novelty is literally encoded in the geometry. It's a vast, diverse, but potentially less coherent state space.
Finally, the PMH makes a very specific and, I think, novel prediction regarding what they call minimally differentiated states.
Yes, like certain advanced meditative states or deep flow states.
This configuration is unique. It's defined by low delta, so the focus is single-pointed, the repertoire is constrained, and high gamma, the neural activity, is highly synchronized, maybe in the theta or alpha bands, and variable I.
Right.
Why is this prediction so important?
Because classic theories might predict that low differentiation means you're becoming unconscious. Less complexity equals less consciousness. But the PMH says no. The high coherence combined with the low differentiation results in a powerful geometric contraction toward low curvature, minimal volumes of manifolds. The experience is highly simplified, unified, and tightly constrained.
So the volume V of the experience space shrinks drastically, but consciousness is still very much present.
Precisely. They hypothesize that practitioners reporting unified or non-dual states should show a differentiation, delta, that's less than 50% of their baseline. But their coherence, gamma, should be greater than 75%.
And what does that do to the geometry?
It results in a phenomenal space where the volume V is less than 20% of the baseline wakeful volume. It's a conscious state that's defined by its simplicity and intense integration. And this challenges the notion that consciousness must be complex or diverse.
So the manifold contracts, becoming highly simple, almost Euclidean locally.
Reflecting a state of minimal phenomenal content, but maximal stability.
The true value of a theory like the PMH isn't just in describing states we already know about, it's in making unique predictions that force us to distinguish it from its competitors.
It has to make risky predictions.
And the framework sets up explicit critical tests against the three leading theories. Let's start with the face-off against integrated information theory, or IIT.
Okay, the core difference here is the number of geometric drivers. IIT says consciousness is driven by phi integration and its derivatives. That's pretty much it.
It's a single-factor theory at its core.
Mostly, yes. But the PMH says the geometry is independently shaped by three invariants, I, gamma, and delta.
So the critical differential test has to isolate the effects of gamma and delta while controlling for integration.
Exactly. Imagine we can create two states, either in a computer model or biologically. Let's call them System A and System B. And in both systems, the integration measure phi, or a proxy like I, is perfectly matched. They're identical on that front.
Okay.
But System A is engineered to have high coherence, gamma, and low differentiation, delta. And System B is the opposite, low coherence and high differentiation.
What are the resulting predictions from the two theories?
IIT would predict that if the conceptual structure derived from phi is similar, then the phenomenology should be comparable. The subjective quality of the experience should be close.
Because the main driver phi is the same.
Right. But PMH predicts that the geometric properties must differ significantly. System A, with high gamma and low delta, will show low dimension and low curvature. That's the unified, simplified geometric state we just talked about.
And System B?
System B, with low gamma and high delta, will show high dimension and high curvature, the chaotic, diverse state. If the geometry fails to differ when I is matched but gamma and delta vary, then the PMH's multifactorial claim is falsified.
Okay, next up, let's compare PMH to global neuronal workspace theory, or GNWT. This theory emphasizes the global availability of information, the broadcast.
Right. GNWT tends to assume that for consciousness to exist, you need rich content that's globally broadcast across the brain.
And the PMH's prediction about the minimally differentiated state directly challenges this assumption.
It does. We just discussed that state of high global coherence, gamma, and low differentiation, delta, leading to a minimal volume consciousness, like in deep meditation.
GNWT would struggle with that because it would interpret the high coherence as a successful global broadcast. But the low differentiation means the content itself is extremely simple.
And that's the test. If we use, say, 10 Hz transcranial alternating current stimulation, or TACS, to induce very high gamma, a strong global rhythm, and we simultaneously reduce delta, perhaps with a specific drug or task.
We see.
PMH predicts a low phenomenal complexity, a conscious, unified, but very simplified experience. GNWT, on the other hand, would probably predict rich conscious content, assuming the global broadcast system is working so efficiently. If we reliably find simplified conscious experiences under conditions of maximal global synchrony, it supports PMH's geometric classification over the standard GNWT interpretation.
Finally, the comparison to predictive processing, or PPPP, focuses on prediction error.
That's right. PP states that phenomenology, what you experience, is driven by precision-weighted prediction error, or PE.
The surprises.
The surprises, exactly. The PMH views the geometric invariants, I, gamma, delta, as representing the fundamental capacity and organization of the system. These are persistent properties that exist even when momentary prediction errors are matched.
So how do you set up a test where the prediction error is matched, but the PMH invariants are different?
It's tricky, but you could do it. You'd need to find two physiological states, perhaps induced by two different neuromodulatory drugs, maybe one affecting serotonin and the other affecting acetylcholine.
And you'd have to show they result in an equal overall prediction error profile.
Right, matched PE. In that case, PP would predict an equivalent subjective phenomenology because the primary driver, PE, is the same.
But PMH would predict something different.
Yes, because the drugs will invariably alter the underlying informational invariants. One might boost gamma, while the other significantly increases delta. So PMH predicts a distinct phenomenal geometry. If the geometry differs despite matched prediction error, PMH gains explanatory power over PP.
This systematic effort to seek disproof is really the hallmark of strong science, and the PMH lays out 6 explicit falsifiability criteria. Let's just touch on a few of these, beyond the differential tests we just covered.
Okay, the first and most basic structural test is the requirement for geometric consistency across subjects. The theory posits a universal structure. That means the intrinsic dimension n has to be consistent.
So if your brain during quiet contemplation has an intrinsic dimension of 10, and mine has one of 25 under the same conditions,
then the theory is fundamentally flawed. If n varies wildly, say, the variance exceeds 20% across healthy adults under identical conditions, the idea of a shared phenomenal manifold structure fails completely.
Another crucial one is the failure to reconstruct known phenomenology.
This is a validation check. The map pi has to be validated against things we already know really well. If researchers use the PMH machinery to reconstruct a well-known space, like the standard Munsell color space,
the results have to match what we already know about color perception.
Exactly. The distances encoded by the predicted metric must correlate strongly with known psychophysical laws. If the reconstruction violates that known structure, for example, if the geometry places the experience of red-green as being closer than red-orange, the projection map and the metric are deemed invalid.
And maybe the most important for scientific integrity, independence from phenomenological construction. This prevents the whole exercise from becoming circular, from just describing the data you put in.
This test demands predictive power, not just descriptive fitting. The protocol is strict. Researchers have to build the phenomenal manifold using a training set of stimuli, let's call it set A. Then, using only the neural geometric properties derived from set A and the map they learned, they have to predict novel behavioral outcomes, like confusion matrices or reaction times, for a completely new set of stimuli, set B.
And the prediction has to be accurate.
Very accurate. The predicted outcomes must correlate strongly with the actual measured behavioral outcomes, with a required correlation coefficient of R greater than 0.6. If the neural geometry cannot predict novel phenomenology with this level of accuracy, the theory offers no added predictive value. It's just a fancy description.
These constraints, from consistency in dimension to predictive accuracy on new stimuli, make the PMH an extremely high-stakes scientific endeavor.
Now, while the PMH is highly structured and very ambitious, it is not a complete theory of everything, and the authors are refreshingly transparent about its limitations.
First and foremost, the big one. The hard problem remains.
It absolutely does. This is its philosophical constraint. PMH is a theory of structure and correlation. It provides testable laws for how the structure of conscious experience relates to the structure of neural information.
But it doesn't say why.
It's fundamentally agnostic on the ontological question of why those informational structures result in subjective feelings at all. It takes a position of structural realism. We can characterize the measurable shape of the world, but not its fundamental substance.
So they are mapping the rules of the game without knowing who or what invented the game.
That's a great way to say it. Another limitation is its current focus on static states. The framework primarily analyzes states as fixed points in psi.
But consciousness flows. It changes moment to moment.
Of course. And extending it to cover temporal dynamics is a massive future task. They need to develop time-dependent metrics to analyze phenomenal flows, trajectories of thought, and how the system settles into or escapes from attractor dynamics. That would be essential for understanding things like attention shifting or dreaming.
Shifting to the practical challenges, the empirical hurdles are immense. You mentioned the difficulty of estimating it earlier.
The challenge of reliably estimating the intrinsic dimension, n, is substantial. This is because dimensionality reduction techniques require a number of samples, n, that often needs to scale exponentially with the dimension.
So n has to be greater than 2 to the power of n.
Roughly, yes. So if the true dimension of wakefulness is, say, 15, collecting the necessary number of reliable, consistent data points becomes a staggering task.
And the computational cost of integration of I remains a bottleneck.
It does. Even though they use proxies, the ideal measures like phi are computationally intractable for large networks. This means all current operationalizations of integration carry systematic errors, sometimes substantial ones. It forces a trade-off between computational realism and theoretical purity.
And of course, the unavoidable reality check, the reliance on subjective reports.
It cannot be avoided. The entire framework rests on the integrity and consistency of subjective, noisy, and potentially biased phenomenal reports that are used to construct SciEmp. While the validation protocols help mitigate this, we have to always acknowledge that cross-subject variability in cognitive style, memory, or language remains a soft point in the empirical foundation.
Despite these limitations, the potential practical impact and application is vast, particularly in the clinical realm.
The ability to quantify consciousness geometrically provides immediate translational value. Geometric markers, dimension, curvature, volume could offer objective measures for diagnosing disorders of consciousness.
Like coma or vegetative states.
Exactly. If we can reliably show that the manifold collapses to ND3 in deep sleep, and we find a patient in a vegetative state also shows NE3, that provides a quantitative structural marker that is independent of a subjective behavioral response.
This could also revolutionize real-time monitoring, like during surgery.
Absolutely. Anesthesia monitoring currently relies on proxies like electrical power changes. The PMH offers the possibility of real-time tracking of phenomenal depth by monitoring these geometric markers. A sudden collapse in NMV could provide an earlier, more reliable warning of deep unconsciousness and reduce the risk of accidental awareness during surgery.
It moves psychiatric and neurological diagnosis from descriptive checklists to structural quantification.
That's the hope.
Finally, let's return to the implications for machine consciousness. If we are defining consciousness by its geometric structure, the PMH gives us clear, testable criteria for artificial systems.
It moves the discussion from the philosophical, is the AI suffering, to the engineering question, does the AI possess the necessary geometric capacity?
And PMH provides operationalizable thresholds.
It does. Three of them. First, does the system exhibit minimal integration? IS has to be greater than some minimum value, which they estimate around 0.15 bits. Second, is the intrinsic dimension of its activation manifold sufficiently complex, isn't greater than or equal to 3.
And
Third, does its metric, its GPC, obey the structural constraints imposed by the invariants? Is it being shaped by integration, coherence, and differentiation in the right way?
if an AI meets these geometric criteria that we know correlate with biological consciousness, the implications are immense.
The PMH suggests applying the precautionary principle. If an artificial system meets the geometric criteria that correlate with human consciousness, we should probably treat it as potentially phenomenal until proven otherwise. This forces us to define a quantifiable structural checkpoint for AI ethics and regulation, moving the discussion squarely into the realm of measurable engineering. #outro.
This deep dive into the phenomenal manifold hypothesis reveals a theory that is methodologically demanding but also structurally profound. I think the most important nugget we can take away is the fundamental shift in perspective. Consciousness is not merely a computational output. It is a quantifiable, measurable geometric structure, a shape that is governed by the interplay of integration, coherence, and differentiation.
And by combining those local constraints of neural precision with the global levers of the informational invariants, the PMH provides a universal quantitative language. If we can accurately measure the intrinsic dimension, the curvature, and the volume of this phenomenal manifold,
We gain a scientific tool.
a tool for comparing every possible state of mind, from the simplest dream to the most complex machine intelligence, all on the same geometric playing field.
And this leaves us with the ultimate provocative challenge, a task for the future of engineering and neuroscience. Determining the minimal architecture required to support a structured manifold with an intrinsic dimension of, say, n greater than or equal to 3.
Can we design a simple non-biological substrate, maybe a minimal artificial network or a synthetic circuit, that can achieve that specific balanced combination of I, gamma, and delta needed to produce complex, high-dimensional, phenomenal geometry?
And if we succeed,
If we succeed in engineering that geometry in a non-biological substrate, it forces a profound answer about whether the fundamental laws of consciousness are dependent on biological matter or if they are purely a function of geometric organization.
the PMH has provided the geometric roadmap. Now the construction begins.